lecture, we have discussed the linear operators on a vector spaces, operators on vector spaces. So, this operator we have defined as t of x plus y is equal to t x plus t y and t of alpha x equal to alpha of t x, where the domain of t t is a vector space and range of t lies in a vector space, lies in Y, which is a vector space. Okay, so, that way we have defined the linear operator on a vector space, say x, t an operator from x to y. Okay. Now, if we look the definition here, we are having the two operation addition and scalar multiplication. So, this operator t has a connection between a scalar multiplication and addition of the two vectors, but we do not have anything about the norm. So, if I replace the vector space x by a norm space or a Banach space, then this norm has no function over here so far. So, we wanted to extend this concept of the linear operator over a Banach space or over a norm space, which includes another operation which we call it as a norm. So, a operator which includes all these three operations, its definitions, will be more interesting and important comparative to this one, and this leads to the concept of bounded linear operator. The bounded linear operator is defined as follows: let x and y be norm spaces, Here I am taking the same norm and can use the another notation as this as norm x and this is corresponding to the norm y. So, normally we do not write it because it is a understanding that whenever the elements of y is there, the corresponding norm of y is used. So, let x and y be norm spaces and t is a mapping from domain of t, which is of course a subset of x, to y, a linear operator. Then we say the operator t is said to be a bounded linear operator, said to be bounded, a linear operator said to be bounded if there is a real number C, of course, C will be positive, such that for all x belonging to domain of t, the norm of t x is less than equal to C times norm of x. So, we have defined the bounded linear operator in this way, means a linear operator is said to be bounded if this extra condition is also satisfied. So, basically if we look, an operator t from domain dt to y is a bounded linear operator, means that this should satisfy this condition alpha x plus beta y equal to alpha of t x plus beta of t y, that is t is linear, and apart from this the norm of t x should be less than equal to C times norm of x. Here this is the norm on y and this is the norm on x. So, this gives the relation between the norms and the operator also. So, this operator, an operator which satisfies these conditions, we call it as a bounded linear operator. Now, the question arises, what should be the minimum value of C here, so that this condition holds? This can be obtained as a, since norm of T x by norm of x is less than or equal to C. This is true for all x belonging to domain of T dt. So, take the supremum of this norm of T x over norm of x, and x belongs to the domain of T. If this supremum, that will be the minimum value of C, which will be satisfied by this. So, this we denoted by norm of T. So, let norm of T is this, which is the minimum value for C. So, if I take it here is, then this minimum value of C, we call it as a norm of the operator, of the bounded linear operator T. Clear? And if we use this thing against him, so we get the relation that norm of T x replaced by the minimum value norm of T into norm of x, and this is a interesting relation which will be used very frequently. So, we get from here that this norm of this is like this. Now, if T is 0, because 0 is also a bounded operator. So, if T is 0, here one more thing which I write, that for all x which are different from 0, where, because if x is 0, we cannot divide by this. So, for all x which are non-zero, the minimum value of C will be defined like this. So, x is not equal to 0. Okay? So, this will be T is, if T is 0, then the norm of T is considered to be the 0. So, we do not take it always. In order to complete the definition, we take it norm T, and when T is 0, it is equal to 0. Okay? Norm T. Then we have certain lemma which will give you the another definition of the norm T. The definition, there is an alternate way of defining the norm, and it is defined as, let T be a bounded linear operator as defined, bounded linear operator, then the norm of T can also be defined as supremum of norm T x, where x belongs to the domain of T and norm of x is equal to 1. Norm of x is equal to 1. This, look the definition, this here the definition of the norm which is assigned by A and the definition of norm which is given by B. This suggests that norm of an operator T is basically obtained by choosing the supremum value at all the point x which are on the unit circle, centered at 0 and radius 1. So, if we take any point here whose length is 1, distance from this is 1, the supremum is taken over all such x, that will give the norm. So, you need not to go for the supremum for the entire domain dt, simply choose the point which has a length 1, those vectors which has a length 1. Okay. Let us see the proof of this lemma. So, proof of this lemma, this is a very simple way. Let us suppose norm of x is equal to A, and let us set by equal to 1 by a into x, where x is not equal to 0. Obviously, from here norm of y will be 1, because norm of y equal to norm of x by a is equal to this. So, norm of y is 1, and since t is linear, so we get t of norm of t, which is defined as supremum of norm of t x over norm x when the x belongs to the domain of dt. So, but norm x is 1. So, it is equal to supremum of norm 1 by a norm of t x, where x belongs to the domain dt and norm of x is equal to a. Then this will be x is not equal to 0, of course, x is not equal to 0. Then this will be equal to supremum is taken over all x norm of t x by a, where the x belongs to dt and x is not equal to 0. Because it is a norm, the property of the norm, if you remember, that norm of alpha x is equal to mod alpha. Norm of alpha x is equal to mod alpha into norm x. So, using this property, we are able to write this 1 by a inside and we get this. But x by y is by. So, basically this is the supremum of norm t y, where the y belongs to the domain of dt and norm of y is equal to 1, and this proves the results for it. So, the norm of a bounded linear operator one can define in this way as the supremum norm of t x over norm x, x belongs to the domain of dt and x is not equal to 0, or equivalently we can also say equal to supremum norm of t x over all x belongs to dt, where the norm x is equal to 1. Clear? So, either this way or B. Now, the question whether this really satisfy the condition of norms. So, if we look at conditions, this norm satisfy norm of t satisfies the conditions of norm. Why? Because the first condition is obviously true, norm of t equal to 0 if and only if t equal to 0. Because if it is 0, then according to this supremum has to be 0 for all x belongs to this. But if norm of t x is 0 or norm of t y is 0 for all y where y is norm y is 1, then it is only possible when t is 0. So, vice versa. So, norm t equal to 0 implies t is 0, and similarly if t is 0, this entire part will be 0 and we get norm t is 0. Second condition which we can see, the norm of alpha x where alpha is this. So, supremum norm of t alpha, this is alpha t, sorry, alpha t. So, this is equal to alpha into t x. So, alpha x we are taking, okay, alpha t, or you can write this, sorry, let me see, norm of alpha t, by definition it is the supremum of norm alpha t y. I am taking the second definition, y is dt, norm y is equal to 1, but alpha can be taken outside and we get mod alpha norm of t. Similarly, the third condition one can prove that norm of t 1 plus t 2 is less than equal to norm of t 1 plus norm of t 2, because the supremum of the sum is less than equal to sum of the supremum. So, this can be verified. Therefore, all the three conditions are satisfied and this gives a norm, and equivalently this gives the norm for it. Okay. So, this one. Now, there are certain examples. There are examples for the bounded linear functional as well as unbounded linear functional. So, first example of the bounded linear functional, the identity operator. As we have seen, the identity operator I is a mapping from x to x on a norm space x such that on a norm space which carries the image x to I x that is equal to x. And obviously, it is a linear operator and bounded also, because the bound of this we can see it is 1, norm of this is 1, or easily verified. Okay. Then 0 operator, this is also a bounded linear operator, a 0 from x to x which carries the image x to 0, and it has a operator bounded with a bound 0. The third operator, which is a differential operator, we see that this operator we have seen is already a linear operator. That is, if we take x to be the norm space of all polynomials on the closed interval 0 1, on the closed interval 0 1 with the norms given as norm of x equal to maximum of mod x t and t belonging to the interval 0 1. Now, differential operator t is defined on this x as t x t is the derivative of x with respect to t. T x t is the derivative of x with respect to t, where the prime denotes the differentiation of x with respect to t. Now, we can see quickly that t is linear. This we have already shown earlier, t is linear. Now, to show whether t is bounded or unbounded, let us check. We claim that this operator t, differential operator t, is unbounded operator, is not bounded. It means we are unable to get a constant c such that norm of t x is less than or equal to c times norm of x. Let us see, for example, suppose I take a sequence of the polynomials functions x and t as t to the power n, where the t belongs to the interval 0 to 1. This is a polynomial, so it belongs to the class, and find out the norm of x n. By definition, the norm of x n will be equal to 1 because the maximum value is taking. So, norm of this is 1, fine. When we operate this t of x n t, the operation will give derivative of x n t with respect to t, and that becomes n t to the power n minus 1. So, the norm of t x n, because it is also a polynomial, so norm is defined as the maximum of this. So, it will be the n into the maximum value of this t to the power n minus 1 when t belongs to 0 1, and that is nothing but n. Okay. So, what we get it here is that norm of t x n divided by norm x n, that will come out to be the n. Now, as n increases, the bond c, this is equivalent to c, the c which is equal to basically n increases. It means we are not able to find a constant c such that norm of t x n is less than equal to c times norm x n for all n. It is not possible, we are not able to get. So, this shows that t is unbounded, is not a bounded operator. Okay. So, what we see, this is a very interesting example. Why in the interest? Because the differential operator is a very frequently used operator, and entire real analysis and concept is based on this continuous and differentiation. So, this operator, which is an unbounded linear operator, suggests that the theory of the unbounded linear operator plays a vital role in the development of the analysis or functional analysis or any branch of mathematics. We have a lot of application of an unbounded operator and one of them. Okay. So, we have also come across about the integral operator. What is that integral? That suppose t is an operator from C01 to C01, where C01 is the set of all continuous functions defined over the closed interval 0 1, set of all continuous functions defined over the closed interval 0 1. So, if we take a point x here, the corresponding value y is coming to be in the form of t x, which is also continuous, where the y we have defined as integral 0 to 1 k of t tau x tau d tau, where k is known as the kernel, is a given function, which is called the kernel of the operator t, and we assume that k is continuous on this closed square, on the closed region or square j cross j, that is on 0 1 cross 0 1, 0 1 cross 0 1 in the t tau plane. Okay. So, this definition, this way, when we define the operator t, which maps the x to y, where y is defined in this way, is known as the integral operator. Now, we claim that this operator t is linear and bounded. Linearity follows immediately just by replace x equal to alpha x plus beta y. So, here it will change the alpha x tau plus beta x tau, and then it can be break up as a sum of the two integral. So, linearity of the operator t is guaranteed. To show the boundedness, let us see, the function is continuous function, and the norm on C01, let the norm on C0 is defined as, or is considered as, the norm of x as maximum of mod x t dt, where mod x t solely and t belongs to j. Because there are two ways in defining, one is this way, another one is the integral form. We are choosing the norm on this form. Now, once you take this, then t is bounded obtained from here. What is the norm of t x? Norm of t x means it is equivalent to the norm of y, but norm of y is the maximum of y, means this part, this is it not? So, maximum of mod by t, where the t belongs to j. But maximum of by t, this is equal to, so norm of T x, norm of by, which is norm of T x, is equal to the maximum of t belongs to j modulus of integral 0 to 1 k t tau x tau d tau. Okay. Modulus, use the modulus, so it will be less than equal to maximum of t belongs to j integral 0 to 1, take the modular inside, mod of k t tau into mod of x tau d tau. Now, k is a continuous function. Since k is a continuous function, by assumption on the closed region, on closed region j cross on a closed region j cross j, is it not? On this closed region the function is continuous. So, it is bounded function. Every continuous function on a closed region is bounded. So, k is bounded. K is bounded means we can find a bound for a number, say m, which is positive, and mod of, so that mod of k t tau is less than or equal to m for all t tau, for all t tau belongs to the region j cross j. Okay. So, this is true boundary. Hence, from here we can say the norm of T x is less than or equal to, this will be m, and what will be this maximum of this norm of x t is the norm of x, that is all. So, we get this one. Hence, this shows that T is bounded operator. Okay. So, integral operator comes out to be a bounded linear operator. Yes. Now, yesterday we have also taken one example of the matrices, and matrices we have considered. In fact, it comes out to be an operator, that if A is a matrix of order m cross n, then it behaves as an operator from R n to R m, R n to R m, such that the image of x goes to y, where the y is equal to A x, and is defined as, if we choose x to be xi 1, xi 2, xi n. So, if we take x to be xi 1, xi 2, xi n of order n cross 1, y equal to eta 1, eta 2, eta m of order, say m cross 1, then A x y is equal to A x will give y equal to A x will give the eta I sigma A n k xi k, k equal to 1 to n, and that will give the eta A n k. So, eta n a I k, here I am taking I, sorry, this is I. So, it will be written eta I as sigma A I k xi k, k is 1 to n, like this, where the I will varies from 1 to m, 1 to m. Okay. So, this will be our corresponding one. Now, let us see the matrix A. We have seen matrix A is linear. Now, we also claim A is bounded. It is not only linear, it is bounded. Why? What is the norm of T x? Norm of T x is square. This is equal to sigma eta I square. I is 1 to m, because this y is equal to eta I, and eta I is varying from 1 to n, and it belongs to, so y is equal to eta I of order eta I belongs to R m. Okay. So, the norm will be defined in this fashion, raised to the power half. So, we are getting norm, but eta I is there. So, we are getting sigma I is equal to 1 to m, then sigma k equal to 1 to n, a I k x I k, okay, square x I k square, that is all. Now, apply the Cauchy-Schwarz inequality. So, by Cauchy-Schwarz inequality, we get that this norm of T x square is less than equal to sigma I equal to 1 to m as usual, then sigma k equal to 1 to n a I k square power half sigma k equal to 1 to n x I k square power half, that's power half, and then whole square, because this is square. So, we have applied this Cauchy-Schwarz inequality over the product of these two things. So, sigma of, if these are a I k and x I k, they are non-negative numbers, then we are getting this sigma a I k this square into power half sigma x I k square power half, and then square will be there. Okay. Now, this shows from here that this is equal to, now this part is what? This is basically is equal to norm of x. So, we are getting this is norm of x square into double summation I equal to 1 to m, k equal to 1 to n, a I k square, and square will get. Now, this is nothing but simply a constant. So, let it be replaced by another constant, say c square into norm of x square. Therefore, we get from here is that norm of T x is less than equal to c times norm of x. So, T is bounded. So, every matrix of order m cross n represents a bounded linear operator from R n to R n. That's and this way finite case is very simple, because we are dealing basically the matrices. Okay. Now, there is another advantage of the finite dimensional norm space, that so many concepts are valid for a finite dimensional case. Just like in we have seen earlier, if the two norms are equivalent, then over a finite dimensional case the topology generated by these two norms will be the same, but this may not be true in case of the infinite dimensional case. So, here also there are many results which are valid for a finite dimensional case in general, but may not be true in a infinite dimensional case. So, one of them results we are telling is that if a norm space is a finite dimensional, then every linear operator must be bounded. What result is, if a norm space is finite dimensional, norm space X is finite dimensional norm space, then every linear operator on X is bounded. Okay. Let us see the proof of this. In case of the finite dimensional norm space, any linear operator is a bounded operator. The proof of it. Suppose we take x to be finite dimension. So, let the dimension of x be n, and E1 E2 En be the basis element basis for x. So, any element x belonging to capital X can be expressed as sigma alpha I x I alpha I E I, because E1 E2 n all basis element, I equal to 1 to n. Okay. But T is linear, T is linear. So, the image of x under T becomes sigma I equal to 1 to n alpha I T of E I, T of E I. Okay. Therefore, norm of T x is less than equal to sigma I equal to 1 to n mod of alpha I into norm of T I, T E I. T1, T2, Tn, these are the finite in number and norm we are taking. So, this is the length of the vector Ta1, T2, Tn. Replace this by a maximum value. So, let it be a m into sigma I equal to 1 to n mod of alpha I, where m denotes the maximum value of norm T E I, where I is varying from 1 to n. Okay. So, we are getting this, let it be equation 1. Now, since x is can be is expressed as I equal to 1 to n alpha I E I, where E1 E2 En these are the linearly independent set of vectors, because these are the elements of the basis. So, for a linearly independent vector, we have seen that one result, that if E1 E2 n are linearly independent vectors, then one cannot expect a vector involving the large number of scalars, but a minimum length. That is, one can find a constant C all epsilon r such that norm of this is greater than equal to epsilon r times sigma of this. So, we get from here is the norm of x, which is equal to norm of sigma alpha E I is 1 to n, and again apply this. So, there exists a constant C such that this will condition holds by the earlier lemma proved earlier. Okay. This is the lemma proved earlier. So, from here we get sigma mod alpha I is 1 to n is less than equal to 1 by C into norm x. Let it be 2. Now, if we combine first and 2, one is norm of T x is less than equal to this, 2 is sigma alpha is less than. So, 1 and 2 gives that norm of T x is less than equal to m by C into norm x. That is, there is a constant, some constant this which is. So, this implies that T is bounded. So, every linear operator in a finite dimensional case is a bounded linear operator, and that's. Now, since the linear operators, they are basically a mapping. They are a mapping, only difference is that when we operate from vector space to a vector space, then this is called an operator. So, whether vector space is replaced by the norm or a Banach space, again this is a mapping. So, in case of the mapping, we have a concept of continuity So, similar concept we can also define over a bounded linear operator, over a linear operator, or in general an operator when the operator will be considered to be a continuous operator at a certain point or over the entire domain T. So, we define the continuity of an operator, continuity of an operator, continuous operator, okay, operator. So, let us suppose T is an operator from dt to y, not necessary to be linear, not necessary linear, any arbitrary operator, that is all, where the dt is contained in x, x is a vector space and y is also a vector space or norm, where x and y are choosing to be say norm space spaces. Okay. We define the operator T is said to be continuous at a point x naught belonging to the domain dt if for every epsilon greater than 0 there is a delta greater than 0 such that the norm of T x minus T x naught is less than epsilon for all x belonging to the domain of T, satisfying the condition norm of x minus x naught is less than delta. So, its definition is parallel to our definition of the continuous function. The only thing, the mapping is f is replaced by operator T. So, an operator for which this condition is satisfied, that for any epsilon one can identify a delta such that difference between the images remains less than epsilon provided the differences between the points is less than delta. Now, if x naught is an arbitrary point, if this is true for all entire points, all the points of dt, then we say T is continuous over the range. So, we say T is continuous if T is continuous at every x belonging to domain dt. Okay. So, clear. So, we now if an operator is a continuous operator and operator is also linear, operator is bounded, these three concepts we have introduced. What is the relation between these three concepts? The very interesting result we can now say that in case of the linear operator, the continuity and boundedness comes out to be the same. Okay? Because in general in a function is continuous, it will be bounded over, if a function is continuous over a closed interval, it will be a bounded function. But if the function is bounded, then it need not be a continuous function. Okay? But here the continuity and boundedness will be identical when T is a linear. And another point which I want to make it clear, the concept of the boundedness of a linear operator and the concept of the boundedness of a function is different. In case of the function or mapping, we say a function is bounded when the corresponding range set is bounded. But here we do not talk about this thing. What we say, a operator is bounded when this satisfies the certain condition. The condition is the norm of T x is less than or equal to c times norm of x. That is the image set. The image is norm of T x, so length of this vector divided by the norm of this original vector, if we take the supremum of this must be some number c greater than 0. Supremum must exist for it, then we say it is a bounded operator. Okay. So, we have now a relation between this, and the relation is in the form of result we say theorem. Let T be a operator from dt to y be a linear operator. Where dt lies in x and y both are norm spaces. Norm space. Then one T is continuous if and only if T is bounded. Second one, if T is continuous at a single point, then it is continuous throughout the domain D. It continues on dt throughout the domain D. So, in case of the linear operator, this is also second result in testing, that to test the continuity of the entire domain, just simply find the continuity at a single point. Because the T is linear, it will automatically spread the continuity over the entire domain dt. The proof suppose T is 0, case 1, then nothing is proved, everything is very obvious, because in case of the 0 operator, which is a linear operator, continuity and boundedness will be the same. So, it will nothing to, so it is obvious, T's statement is obvious, okay, or trivial. So, let T is not equal to 0. Okay. Now, assume, so we wanted to prove first thing A. So, assume T is bounded, we wanted to show T is continuous, T is bounded, given T is linear, this is known already, linear. Okay. To show T is continuous, okay, T is continuous. So, suppose x naught be an point in the domain dt, okay, and let epsilon greater than 0 be given. So, for the continuity means we have to find a delta such that norm of T x minus T x naught less than epsilon only when x minus x naught less than delta. Okay. So, since T is linear, so for every x belonging to the domain dt such that norm of x minus x naught less than delta, where delta I am choosing to be epsilon over norm T, be obtained, we get norm of T x minus x naught, this is equal to norm of T x minus T x naught, which is less than equal to norm of T into x minus x naught, okay, and this is less than equal to norm of T, and x minus x naught is less than epsilon over norm T. So, it is less than epsilon, it is basically equal here. Okay. It means that if I choose an arbitrary point x naught and epsilon greater than 0, then because T is linear, this condition can be written. t of x minus x naught can be written as t of x minus x naught, and because t is linear by this and bounded, as also because of the boundedness we can write from here to here, because norm of t x is less than or equal to norm t into norm of x. So, from here we can write this thing, and again epsilon is chosen. So, we can find a delta in terms of epsilon, which is equal to epsilon by norm t. Substitute it, we get this thing. Therefore, what we conclude is that t is continuous at x naught. Okay? But x naught is an arbitrary point. So, we can choose any point. Therefore, t is continuous over the throughout continuous on dt, throughout the domain dt. Okay? Now, let us see the converse part. Conversely, what is given now, that we wanted the t to be bounded. Okay? So, t is given to be continuous, given t linear and continuous on at an arbitrary point x naught belonging to dt. Okay. So, by definition, then for given epsilon greater than 0, there will exist a delta which is depends on epsilon greater than, such that norm of x minus x naught is less than delta norm of x minus, such that norm of t x minus t x naught is less than epsilon for all x belonging to dt, satisfying this condition, norm of x minus x naught less than delta. This is by definition. Okay. So, now choose the point y, choose any y different from 0 in dt. Okay. And let x is, suppose, x naught plus delta over norm y into, since y is not equal to 0, this is 0. Okay. Y is not equal to 0. So, we can choose like this. Now, from here obviously x minus x naught norm y is delta. Okay. This. So, by definition of continuity, therefore, t x minus t x naught, this is equal to norm of t x minus x naught, because the t is linear. Okay. Then this will be equal to norm of t x minus x naught, you can write it delta over norm y into y. Okay. And this will be equal to, now since t is, okay, t is given to be a this continuity is satisfying, t is continuous. So, this has to be less than epsilon for whenever the norm of this thing is there. So, we can say this part is less than epsilon. So, we are taking this delta over norm y out into t of y. Okay. Now, this is to be less than epsilon as t is continuous. Okay. So, from here we get norm of t y is less than equal to norm of y over delta into epsilon, and that is shows that this will be equal to, that is norm of t y is less than equal to constant times norm y, because this is nothing but simply a constant. Therefore, t is bounded. Okay. So, this shows that t is bounded. So, this proves the result. The second part is very obvious. Second part, what it says is that if it is t is continuous at a single point, it is continuous on this. So, if support T is continuous at the single point, then according to this must be bounded. Bounded means throughout the boundary, so it is continuous again at any RBT point, and this proves. Okay. So, second part follows very easy. Thank you.